Okay, so, all right. Okay, so let me tell you, okay, so there's this engineer. He was walking, and he comes upon a frog, okay? So the frog says, if you kiss me, I'll turn into a princess. And he picks up the frog and puts it in his pocket. It's a male engineer, because that's why I'm saying he. So he puts it in his pocket, and then he continues on the way, and the frog says, I'm a beautiful princess. If you kiss me, I'll turn into a beautiful princess, and I'll stay with you for a week. And the engineer just goes about his business and continues. And then the frog says, I'm a beautiful princess. I'll stay with you for the rest of your life if you kiss me, and I'll be a beautiful princess, and we can be together for the rest of your life. And the engineer continues about his business, and so finally the frog asks, why won't you kiss me? I told you I would turn into a beautiful princess. And the engineer says, well, I'm an engineer. I don't really have time for a girlfriend, but a talking frog, that's cool. Okay. All right, so the problem sets will be out later today. We're changing things around a little bit. I decided to put in some parallel stuff, so we were going to add a question about that. If you're dying to know what's on the problem set, I'll just post the problems we have that are going to be for sure right after lecture. I'll post them up, and then there's going to be one more. Okay? All right, so okay, apparently that joke was not so good at settling everybody down. So, okay, next one. Okay, well, I have the midterm times in my inbox, so I just need to transcribe them to Piazza. I don't know what they are right now. Okay. Okay, so we're going to review the FFT. We're going to do the inverse FFT, and then we're going to look at the FFT again, okay? And then we're going to look at the FFT circuit, okay? And then we're going to do some parallelism. Okay, so so remember the FFT. We use this notion called the nth root of unity, and the nth root of unity is in this polar notation. This is what it looks like. There's some nice properties. One of the main ones is w to the I and w to the I plus n over 2 are related, right? Because w to the I plus n over 2 is equal to wi, which is equal to w omega of I omega n over 2. And omega to the n over 2 is the square root of unity, which is -1. So these things are related. This one is basically equal to this one, they're negatives of each other. Okay, so that's the key property, right? So so they have a common square too. So there's two things. One is equal to the negative of the other, and they have a common square. So common squares, and the common squares, moreover, are the n over 2th roots of unity. So we have this thing that's very nice for computer scientists in that we have some sort of invariant at the level n, and we have the same thing at the level n over 2. We were looking at roots of unity and working with the roots of unity, nth roots of unity, and now if we square them, what we get is n over 2th roots of unity. Okay? And we get half as many. Okay, so this is the invariant we have, and we can take this invariant and make this fast Fourier transform algorithm. Well, we want to evaluate a of x on all these roots of unity. We recursively compute all a of e on the n over 2th roots of unity and a of o on the n over 2th roots of unity. And that's why they're squared, a of e omega squared, a of e omega cubed, and so on. And then we can calculate a of omega is, remember, a of x was equal to a of e of x plus omega plus x times a odd of x. Now I'm just plugging in omega to the I here. It's a of e of x squared plus x times a of odd of x squared. So I plug in omega, and And now the key here, the reason this is fast, is I made two subroutine calls. I made this subroutine call, and I made this subroutine call. Okay? A priori, when we did it one point at a time, you think you might have to do 4. 1, 2, 3, 4. But in fact, these two are the same. This subroutine call up here provides information for these. Okay? Okay, so that's why the runtime recurrence was T of n. And now what we need to do is compute the FFT on n over 2 points. Okay, so and we need to do that for the odd polynomial and for the even polynomial. So that's where the 2 comes from, and it's O theta of n to do this particular step, because you're doing a loop over n items. Okay? Yeah. N can't be odd. We're not allowing that. We're assuming that n is a power of 2. We're only going to let you have an FFT for n being a power of 2. Yeah, but you could add zeros to the other. You can make a polynomial if you have a polynomial with degree 3 or degree 4, then you have 5 coefficients. So I would just make that a polynomial of degree 7 with 0 coefficients here. Okay, so it only changes it by a constant factor. Okay, there's always a power of 2 within a factor of 2 of your thing, so it doesn't change things. Yeah. It's the time to do this, because you're doing this loop, and you're doing n times through this loop. Yeah. Just to compute your answer. There's n points that you're outputting. So each one of these iterations outputs 2 points. Okay? Okay, so is there any more on that slide? Okay, so again, we did this before. I'm just reviewing quickly. So there's the evaluation. So we can do this if the x0 through xn or xn minus 1 are roots of unity. And that was nice, but we needed to go backwards. We need to actually be able to, from this point representation, come back to the polynomial representation. So we want to go from points to a function. Given 3 points, give me the quadratic that fits it. Give me the polynomial that goes through those 3 points. Okay, that's what we're saying. Given n points, give me the polynomial that goes through those n points. Okay? So how do we do that? Again, we need to re-examine what we did. If we want to undo what we did, let's see what we did. Okay, so this is what we did. We just basically wrote it as a matrix multiplication. You can write out this polynomial evaluation as this matrix multiplication, and this is the matrix that you put in. Okay, again, this row is times this column. Okay, this row here, the first row with x zeros times this column here is going to give you a0 plus a1 times x0 plus a2 times x0 squared plus a3 times x0 cubed. That's just evaluating the polynomial on x0. Okay? And so on. So this is the matrix. So we multiply the matrix. It's slow, but of course we have our, if we actually use this matrix, we already saw that we could compute the function evaluations for this matrix. This is what we did with the FFT. So that is fast. Okay? So now what we want to do is compute the inverse of this matrix. So we're defining this matrix to be m sub n of omega. It's a matrix that we implicitly, somehow, ingeniously calculated fast, right? The size of the matrix is n squared. We never even wrote down the matrix, right? Somehow we computed the effect of multiplying by this matrix without ever writing it down. Okay? Yeah.
I'm still confused why exactly this matrix is faster than the other.
Well, because we have an algorithm that computes the answer. The FFT computes the answer. There's nothing, you write out the matrix, but the FFT just computes the answer.
So why exactly?
I'll show you again. We're going to go over it again. We're going to do the FFT again and again and again until you never ever want to see the FFT again. Okay? Already don't want to see it? Oh, come on. Okay, so Okay, each row is orthogonal in this thing. Is that clear to you, that if you take a dot product of this row and this row, it's orthogonal? The first row and the second row? Is that clear to you, that that's orthogonal? Why is it clear to you? Because it was problem 2.7, right? That was problem 2.7. The sum of the second row items is 0. That's what problem 2.7 was, right? And when you take the dot product of the first row and the second row, that's what it's saying. It's saying, you know, you sum up the second row because it's all ones in the first row. Okay? So essentially, your homework, you showed this orthogonality of the rows, right? Yeah. Yeah. All the dot products between two different rows are 0. Okay, so I'm going to do, so each row is orthogonal, and I showed you this picture before if it's helpful. In linear algebra, you should have seen this sort of thing. If all the rows are orthogonal, you're really just basically rotating the whole basis in something like this fashion. Okay, you also might be scaling it in different ways, so I'm ignoring that. I'm assuming the scaling is all the same. Okay? All the vector lengths are the same. All the row lengths are the same. And so how do you do it? You do the inverse rotation. And also from linear algebra, you should know you just basically take the transpose. Okay, but yeah, so one caveat, this is not quite a rotation because what's the length of a row? The first row, we can see the lengths of all the rows, but the first row has length n, and all of them, with the easy calculation, you can see all of them have length n. So you have to scale it by n. It's square root of n, but you need to, yeah, it has Euclidean length, square root of n, or, yeah. I mean, it depends on what you call length, but yeah, that's the standard way to do it. Okay, so then you want to project it and project it back, and axis should have the length 1, FFT, the length. So it's a little bit, it doesn't quite just rotate it. It rotates and it blows it up, makes it bigger. So it spreads it out. First it rotates and then it spreads the points out. That's what this matrix does. So you need to do the opposite when you come back. So that's what we're going to do. So what we're going to show is that the inverse of this matrix, of the FFT matrix, is just 1 over n times m of, essentially the FFT matrix with one little difference. What's the difference in the second term here? The 1 over n is there. Okay, but what's the difference of the matrix itself? What's the difference in the matrix? Yeah, it's omega to the minus 1. Okay? So it's omega to the minus 1. Okay, already you're like, well, so is omega to the minus 1 very different than omega? Well, it's different in a sense, but it has very similar properties, right? If omega is the basic root of unity, omega minus 1 is also a basic root of unity, right? There's n, and if you take the square of it and the cube of it and the fourth power, there's exactly n of them that are different. It has all the same properties. If you take omega to the minus 1 to the n over 2, you get negative 1. Okay? So every property we use for the FFT to compute m of n, multiplying by m of n of omega quickly, we can also use for m of n of omega to minus 1. So this calculation of the inverse, of multiplying by the inverse, is just the FFT again. Except instead of using omega, you use omega to the minus 1. And then you need to do one more step. You need to multiply by 1 over n. That's not very hard, right? You can multiply a vector by 1 over n quite easily, right? It's just every entry you multiply by 1 over n. Okay, so this inversion formula is very good. I mean, we are done. We know now if this inversion formula happens to be true, we're done. We have a fast algorithm to do the inversion of the FFT, to do interpolation. Okay, so this is really the punchline. I'm just going to go through the algebra, which basically you already did in your homework. Okay, so what I'm going to do is, how do I know if it's an inverse? Well, m of n of omega times m of n of omega minus 1, for that to be for m of n of omega to minus 1, what should C be? C, yeah, intuitively it should be the identity, but there's a little scaling factor, right? I scale it by 1 over n there. So it should be n on the diagonals and 0 on the off diagonals. Okay? It should basically be the identity matrix. Okay? Except it has n on the diagonals and 0s on the off diagonals. Okay? Okay, so let's look at Cij. Let's just just go through the work. This is how you multiply a matrix, right? So m of n omega minus 1, the kjth entry is going to be omega to the minus 1 to the kj. Okay, and the kth entry of mn of omega is omega to the ik. So this is just matrix multiplication. Okay, and so we go there. I think that's just adding up the exponents. It's just factoring out in the exponent. Okay, so now if I is not equal to j, we're going to let this r be omega to the I minus 1 minus j. Okay? And you know that r to the n is 1. Why do you know that r to the n is 1? Because they're roots of unity. These are all roots of unity. Right? So now Cij is really just this, it's a geometric sum, right? You're summing over k, for k is 0, k is 1, k is 2, k is 3, and so on. So it's just a geometric sum, r to the 0, r to the 1, r squared. Okay, we all remember from high school what's the result, what is the sum of a geometric sum? Right, we just plug it in, right? This is something we've proven and we know, and so we plug it there. So we have this. Now we know a simple expression for each entry in the matrix, essentially. We just need to plug in the appropriate thing for r. Okay? So now let's look. If I equals j, again, we want the diagonals to be n, and the off diagonals to be 0. Okay, so let's see if that's the case. So in that case, what is r? R, if I equals j, r is equal to w to the omega to the 0. What is omega to the 0? It's 1. So how many of these values do you have? You have n of these values, right? So the sum of 1 n times is n. Okay? I mean, this formula doesn't help much. It's 0 over 0. It doesn't give you any bound here. But this, you can just look at this by inspection. You can look at the sum and say, okay, there's n elements, they're all 1. So it's n. So my diagonals are n, like I wanted them to be. Okay, so now if I is not equal to j, then I have r to the n. Now I'm just going to plug in. I'm just plugging it in, and then I'm switching the exponents, right? And now omega to the n is what? 1. So that's 1 to the n. So this says r to the n is 1 to the n, which is 1, and that means that you get a 1 here. And 1 minus 1 is 0. So this whole thing, and 1 minus this is not 0. If omega, this is not 1. Okay? So in this case, Cij is 0. So the off diagonals are all 0. Okay, this is also something that should have been in your homework. Okay, for C, the diagonals are n, and the off diagonals are 0, and you divide by n to get the identity. So this is an inversion formula. Okay? Okay. So computing the inverse, the FFT works with points like this because those are roots of unity, and omega to the minus 1 is the basic nth root of unity. Okay? So all the properties we needed work for the inverse FFT. Instead of running that procedure with omega, just run that procedure wherever you had omega, put it omega minus 1. Inverse omega to the minus 1. Okay? And so now now we can do evaluation. We can take our two polynomials, a and b. We can do the FFT on them, both. And now we get the point representation of a and b. Then we multiply the points pointwise, and we get the representation of C, the product polynomial. Now we do the inverse FFT, which takes n log n, and we have the coefficient representation of C. Okay, so we have this n log n algorithm for multiplying degree n polynomials. Okay? Okay, and it's really amazing, right? I mean, really, from n squared to n log n, it's still kind of shocking. Okay? Okay, so you can do, what you use polynomials for is convolution, which is this process, right? Digital signal, digital signal processing. It's used everywhere. Many other things. Okay, we're going to see a couple of other things here. Okay, so I think it's cool. Okay, so okay, now we're going to look at it again, and so maybe we'll see another picture. Again, why was it that we could take this big matrix and somehow compute this product quickly? Okay, so I just want to review that with pictures, okay? So the idea is, well, what I'm going to do now is I'm going to group the even and odd columns here. I'm going to pull all the I can pull all the columns forward and I can move the columns around however I want, as long as I also juggle the elements in the row, right? In the end, I just need to unshuffle them to see what my answers are, okay? So I'm pulling all the even columns up front. So every one of these columns is an even column. So it has a form 2 times k, because that's what it means to be even, right? And these guys are 2 times k plus 1, because that's what it means to be odd. Okay, so now an entry here, once you represent it in this way, an entry here the jkth entry was omega to the jk. Here the jth, I'm just moving that 2k entry over here. So this particular entry is omega to this times this, which is omega to 2jk. And this is the same. This is omega to this times this, which is j times 2k plus j. And now that's why the omega to the j comes out front. Okay? Okay, so now what I'm going to do is I'm just drawing a horizontal line. Okay. Okay, so now it's just, this is exactly the same. I've not done anything. I'm just saying, if this row is j, this guy's omega to 2jk. If this row is j, this one is omega. It's just copying this over here where I moved my index j up to here. Okay? And now here's where the magic happens in what I show you next. Okay? Now, if I look at the entry j plus n over 2, you know, this is going to be omega to the 2 times j plus n over 2 times k. Okay, that 2 times n over 2 is going to be n in the exponent. So you're going to have an omega to the n extra here. So this is wrong, what I wrote. But it's right, except for the fact that because there's an omega to the 2jk times omega to the n. What is omega to the n? 1. Now look, this entry is exactly the same as this entry. Okay? And now this one is the same sort of thing, right? Here you have that n over 2, and you get that multiplied by, here that 2k, you still get that omega to the n, so that goes away, the n over 2 part. But now this plus 1 here multiplies you get an additional n over 2 in the exponent, so you get an omega to the n over 2. You get an omega to the n over 2. Now what is omega to the n over 2? Yeah, so that's where the negative comes from. Okay? Okay, so now this matrix looks a lot simpler. It's just not this sort of complicated thing with all these different omegas. In fact, there's a pattern. For every element here, there's a corresponding element here with exactly the same value. For this element here, there's a corresponding element here which is slightly different value. Okay, so now we could write this as a submatrix. We could say, well, look, what is this particular submatrix down here? Well, that is exactly m of n over 2, right? Because down here, all these things are omega squareds. You just put in omega squared everywhere, and then there's a jkth entry. And so this is m of n over 2. This is the recursive problem on half the coefficients, right? Because this matrix here multiplies this part of the column, right? Okay, but you have to then add this matrix times this, which is minus, and this matrix is again the same matrix when you factor out an omega to the j times these odds. Okay? So now we have, yeah, this is the same thing. This is omega to the n over 2 times this. This is the, it's talking to me. Shut up. It just starts on its own. Okay, so then this last step here is that there's the omega j. We're pulling it out, and once you pull out one constant factor out of this whole matrix, again you just get this matrix. It's the same matrix. Okay, but here you're not multiplying it by, you're multiplying this matrix by this part of the column, right? And so that's what you get. So then now it's nice and recursive. You see that normally you'd have 4 submatrices when you do a matrix multiply. But here, you really only, these two are exactly the same calculation. And these two are exactly the same calculation. Okay? So that's where the magic is of how we multiply this whole matrix. We noticed a pattern with this matrix, and we see that, you know, it's very, very structured. Okay? Okay, so now we see it again. We're going to make a circuit out of it. We love FFT. We're going to do everything we can with it, okay? So what we're going to do is we're going to think of these inputs, these coefficients as inputs, A0 through an minus 1, okay? So let's look at this matrix. Now, how would I make a circuit? Well, to this part of what I want to do is I want to compute this. So I'm going to make a circuit to compute that. Okay, that's going to be this circuit here, right? This blue thing, I'm going to compute with this circuit. Okay, however I make that circuit, I make the circuit. And the inputs to that circuit are the evens, right? And this red one, I'm going to make a circuit out of this part, which is actually, again, just a circuit for m of n over 2. It's just different inputs here. The odd ones are input to this one. And now, to finish it, once I've computed the results of this circuit and the results of this circuit, I need to put it together to make my output. And an output may be R sub j. From R sub j, what I do is I take the jth output here, from here, and add it to omega to the j times the jth output here. And that's what I'm doing. For R sub j, I'm taking the jth output here and adding it to the jth output here times omega j. Okay, so there's a circuit. And by the same token, okay, so these slides, I was up till 3 in the morning. Okay, so so I hope they're informative. So this one is the same thing. This guy down here, instead of multiplying by omega to the j, you're multiplying by minus omega to the j here for this output, right? For this output, the rj plus n over 2th output takes the jth output here and takes the jth output here and combines it, but it needs to multiply this one by minus omega to the j. So there's a circuit. Okay, so we could build a circuit out of this thing. Okay, so in fact, you could expand it. Here's the circuit. Here's what I just showed you. It's sort of redrawn. Now I could do it recursively. I could take this circuit and I expand it in the same way. And then I can expand it again. Okay, so this is all also done in your book. Okay? Okay, so this is the FFT circuit, right? So now this is nice, right? We already did a circuit problem, right? Well, on the first homework, we did a circuit problem where we used addition, right? We showed a fast algorithm for multiplication. Okay, so there we tried to get a small depth circuit. Okay, so what's the depth of this circuit, you think, as n, as a function of n? Well, this circuit, what's the depth of this circuit, the one I pictured? Well, this circuit is, the depth of this circuit is 3, but it's also, for a depth n circuit, it's going to be log n, right? So it's a very fast way. You can compute this in hardware in very, very little time, and people actually, they're implemented on hardware all over the place. Okay? Okay, so edges from lower half of you have to be a little careful, remember? Before I said this guy's output, this guy you read straight across, but this guy you multiply by omega to the 4. Okay? So this guy you read, the guys and the evens you don't multiply by anything. The evens are the upper half. And the guys from the lower half you have to multiply something when you add them in. So the FFT circuit is actually, these edges, in addition, these edges do something. They multiply. Okay? And the nodes SCAD, the edges multiply. Okay? So the up edges have this form, and the straight edges have this form. I think, okay? So this is the FFT network. So how deep is it? It's log n levels. So the way you describe it is there's n rows of nodes in level I. Row R nodes are connected straight across to level I plus 1 nodes. And row R nodes are connected to the row that's different by 2 to the I. So here, each one of this node is this is row 1, this is row 2, this is row 3, this is row 4, or this row 0, let's call it 1, 2, and 3. So 0 is connected to something that's different by 2 to the 0, which is different by 1. Okay, and so on. Okay, so then, okay, so okay, that's it for the FFT. So let me give you, well, sort of it. So let me give you a break. Why do mathematicians like national parks? Because they like natural logs. Okay. Okay. So how would you add up n numbers? Okay, one way to add up n numbers is for I equals 1 to n as sum equals sum plus ai, right? That's a really fast way, right? For I equals 1 to n, just add the numbers together. Sum equals 0. Sum equals sum plus a1, sum equals sum plus a2, and so on. Right? That's pretty fast. Okay? So you see the title of the slide. The slide is kind of about parallelism, right? Is that how you is that how you did your circuit in homework 1 when you tried to build a circuit? Did you just add one number in and then take its output and add another number in and take its output? And why not? Would have a long depth, right? So there's some notion that it would be slow to do it if you have all these transistors out there or all these adders out there. You might as well use them so many of them are working at the same time, right? So it's sort of important to design the way you do even such a simple task in a way that maybe if you had more resources, you could actually, have them all working at the same time. Does that make sense? So it's a different algorithm. I mean, in one sense, adding up n numbers is really trivial, right? It's order n right away, sequentially. If you just talk about what we talked about in the rest of this class, there's no better algorithm. You're done. Okay, but we also in the first homework we told you to do this other thing. So why? How do we evaluate that in the cost model or the framework we've set up? So what we're going to do is set up a framework that's where we can evaluate that. Okay. So, okay, so let's see. Okay, so this is O of n time. So you could write a circuit. This is what you guys probably did, is you took your n numbers and you fed them into adders, and then you fed the output of those into adders, and you can do it all in parallel. Each level, essentially, the depth of this network is log n. And so really, the real depth was log n times whatever the size of this adder was. So you had to also deal with that. Okay? So the depth, there's log n of these adders, and these bits are actually getting, even if these were bits in the first place, they start getting bigger, and you have to worry about adders that can handle multi-bit numbers, right? So there's some technicalities here, but log n or log n times the size of the adder number, log of the size of the numbers you're adding. Okay, so you did this. And so So what we had in terms of quality there is we already said, yeah, well, we told you to optimize depth, even though we didn't give so much of a framework to do that. Okay? So, and we also, there's two parameters here. There's the depth of the circuit and there's the size of the circuit. So the size of the circuit is O of n as well. Okay? So those are what we call complexity measures in computer science. Okay? So we call these, when we talk about an algorithm for sequential, we talk about time. Sometimes not in this class, we'll talk about space. Those are complexity measures. That's how many resources your algorithm takes. Here for circuits, the complexity measure is the depth and the size, the number of gates in your circuit and the depth. Okay? Okay, so let's look at another circuit. Okay, we saw another circuit, right? So sequential, the algorithm was n log n. So let's evaluate it in terms of these new complexity measures, depth and size. Okay? So the depth is O of log n, right? That's what we worked out at the very end. And the size is n log n, right? The total number of gates in the circuit there's n in each level, and there's log n levels. Okay? So these are just simple calculations to sort of get familiar with this way of counting resources. Okay? I mean, it's natural, right? If you're going to build a circuit, it should be fast, right? That's why the depth is important, right? Okay, you're going to have all this hardware available to you. You shouldn't have one gate working at a time because the other gates are just sitting there. Okay, so this is the appropriate measure for circuits. Okay? How to build a circuit for, okay, so now we're going to roll up our sleeves. Okay. Okay, so you guys are already sleeping because very few of you will actually ever make a circuit, right? Somebody else makes circuits. I don't know who. They come from the North Pole or something, right? Okay, maybe there's a few of you that will make circuits. So why do we care? How about parallel? Okay, so let's look at something here. Well, let's hope I can look at something. Okay, so let's just... Look what I have. I have processor 0 and I have processor 1. I have 2 processors. Yeah. I can use 2 processors. They're right here for me to use, right? Okay, so here's one way I could use 2 processors. I could run my browser and I could run my PDF viewer. That's a pretty good way, you know. One, I run the browser on one processor, I run the PDF. It's pretty easy, right? So we're not going to talk about that kind of parallelism. That's one of those is called embarrassingly parallel. These are problems that it's obvious. They have nothing to do with each other, right? So you can go ahead and run them on separate processors. Okay, so we're going to talk about algorithms where you actually may have to do some work. You have to piece together the answers. Okay, so we're going to work on that process. Or that methodology. How do we do that? Okay? So, okay. They're everywhere, right? And it's only getting more so. My laptop is 5 years old. I mean, if you don't have a Mac, your laptop probably has 8 processors in it, right? So the thin ones, you know, the thin ones, I don't have that problem. So, okay. So they're oh, that's not what I want to do. Here, just a second. Okay. Okay, so it's everywhere. Okay, so we need to now get a model. Well, before we had a model for a computer, right, it did something that was one step. It did another thing that was one step. So one way to view it is the thing it does is it accesses memory. Usually when a computer does something, it looks at a piece of memory, it adds up, or 2 pieces of memory, it adds them up, and then it writes out the answer. So really, we can sort of think of modeling it all as just how many times do we access a piece of memory. That's one way to sort of model. It's called the RAM model, the random access machine model. You are, for any piece of memory, it costs you one time step to access that piece of memory. You know, it doesn't model caches, it doesn't model any of these things, but it's pretty good for counting steps. Okay, so we're going to do the same thing for parallel processors. We're going to have this notion that any processor can access any memory location in one time step. That's the idea. You have all these processors. In my case, I don't have very many. I have 2, but maybe you have many. We're going to view processors as free. There's a sea of processors out there. They're everywhere. We have a lot of them, okay, for now. You know, and by having a lot of them, that creates a big responsibility, right? When you have a lot of ability, you have big responsibility. Okay, so we have all these processors available to us, and we need to go fast. Okay? We could use them all, yeah. Yeah, they could each access a memory location in one time step, yes. Okay, one process, each of them can't do 2, right? Because each one can do 1. Right, but they, you know, there's some argument about whether they can access the same one or not. But there's a big can of worms once you do it in parallel. And you've seen this actually in 61A. They talked about how you prevent 2 from fighting over the same piece of memory. Here we're talking about a complexity model. We're just saying how much time it takes. Okay. Okay, so it models parallelism. This notion of having as many processors as possible as you want is fine, because we're just trying to see how fast you can make it, even with a lot of processors. Okay, but we do want to, it sort of ignores communication costs, because maybe it's not as, maybe the processors are actually on different chips, and it's more expensive to access some memory and other memories. But we already did that with the RAM model. Okay, so let's look at an algorithm here. So when we evaluate an algorithm, as opposed to a circuit, right? So now we need a new complexity measure here on an algorithm. How many steps does it take? How much total work do you do over all processors? Those are the 2 complexity measures. You have them available to you, but they do charge you to use them. Okay? Okay, so those are the 2 complexity measures. And they're very analogous to circuits, right? So we already saw circuits. The time, if the depth of the circuit is equal to the time on the shared memory machine, right? You could take a circuit, you could take all the processors and simulate the first level of the circuit, right, with that many processors. Then you simulate the second level of the circuit with that many processors, and then the third one, and then the fourth one, and then the last one. And then how much time have you taken? You've taken the depth of the circuit. How much resources have you taken? The size of the circuit. Okay? Okay, so let's think about adding up n numbers now. Now we went through circuits, but now we're just talking about parallel computing. Okay, so how will we do this? We don't want to add the first one. We don't want to sum in the first one, then the second one, then the third one, then the fourth one. What should we do? We saw it in a circuit, but we could actually we don't actually need to simulate the circuit, right? We saw a depth log n circuit. We could do that. But we can write an algorithm that basically does the same thing. So you pair them up. You pair up A1 and A0 and A1, A2 and A sub 3, and so on. And then you add them up, and what do you have now? How big is your list? It's n over 2. So what can you do then? You can keep going. Get n over 4 and n over 8. When does this stop? How many times can you pair up and add? Log n. Okay, so it's a log n depth circuit. Now let's look at the work. The first step is, I don't know whether it's n over 2 or n. These constant factors don't matter, but whatever it is, it's half as much the next time, and half as much the next time, and half as much the next time. So the total work, again, we love our geometric series, is O of n. Okay? Okay, so that's our addition algorithm. This is an introduction to the parallel computing model that at least tells you how to expose what can be done at the same time. Okay, so it may not be telling you everything about how to run a parallel algorithm on a computer, but it at least exposes what can be, what doesn't have dependencies. Okay, Okay, so let's look at some of our other algorithms in this context. Let's look at merge sort. Sort sublists. So we split into two lists, we sort the sublist, then we merge the sublist, right? That was the merge sort algorithm. Okay? So the recursion depth was O of log n, right? We showed that because each time the size of the sublist decreased by 2. So the recursion bottoms out in log n steps. So does that mean our parallel time is O of log n? Why not? Why would you spend more than, he says because at any one, at some level you might spend more than O of 1 time. Okay? So okay, let's see what we do at each level. What do? We split into two lists. That's fine. That's fast, right? Order 1 time. We sort the sublist. That's recursive. So that's not at this level. We're not responsible for what happens there. What do we need to do? We need to merge the sublist. Anybody remember our merging algorithm? So the question is it O of log n time? And the answer is no, because it's written in red. But the merge, and why? It's because the merge was sequential, right? We took these two lists, we looked at the first 2 elements, and we put 1 over here. We took what was remaining on the 2 lists, we looked at the first 2 elements, we put 1 over here. And then we put 1 over here, okay? So that was linear. We made a linear pass over the list. So it took a long time at each level. So the time at the top level is order n. At the next level, it's n over 2. The next level, it's n over 4. So the parallel time is not log n. It's O of n. Okay? That's still better than merge sort, right? Better than sequential. Sequential was O of n log n. Okay, so this algorithm is a little faster, even just straight out implementing it. Okay? Just sort of doing it in a log n time. The parallelism comes from where? You execute both subproblems on different processors. So the parallelism is easy. It's an easy algorithm. It's easy to implement every time you call a subroutine on a list. You call them in parallel, right? Really easy, and you get some benefit. You got a time from n log n to O of n. But it still seems kind of lame, right? You have as many processors as you want. O of n doesn't seem so great. So can you make the merge faster? And the answer is yes, but what are we going to use? Of course, not just FFTs, but back-to-back FFTs, and where each of the nodes are not multipliers, but they're comparison sorters, okay? So it's actually, it kind of has nice properties. But this is called bitonic sort. You could look it up on Wikipedia, and its time is O of log squared n. Now the question is, for sorting, you sort of think, well, the depth, now we're like, can we do better? I mean, already I think an O of n algorithm is kind of interesting, just in practice. But as mathematicians, we want to know whether we could do better. And you can, but you don't really know. Well, you don't really want to know about it, please. Okay, so it took a few years, but there is an O of log n time work algorithm for this. But it's really, actually you may want to know. It's very interesting. It took most of the 80s, along with various other cultural trends. But we did finish that. Okay. An O of n log n. So this is what we call an optimal algorithm. In parallel, we call something optimal if basically the work is the same as the sequential algorithm, and the time is as little as possible, right? Log n, you can't really do faster than log n when you compare 2 items in one step. Okay? So log n is sort of a lower bound on how fast you can go. It is, and log n is the total amount of work you can do. Okay. Okay, so there are optimal algorithms for this, but already I contend that the merge sort algorithm by itself gives you some benefit over the sequential algorithm. And it's easy. It has this nice property. Okay, so what about large integer multiplication? Okay, so do 3 or 4 multiplications depending on whether you want to do Karatsuba or what's the other one? Regular multiplication? Okay. So it's a recursive algorithm. We're going to do the recursive version of multiplication where we split the numbers into n over 2-bit numbers, for each one into n over 2-bit numbers, and then do 4 multiplications there. Yeah. Oh, it is. It's Karatsuba. It was faster because I implemented the other one in code, right? They hard-coded it, right? They hard-coded in C. But it is Karatsuba. If you double it, it's not. It doesn't square. It goes like log base. I don't know what log base 2 of 3 does, so I just run the squared one. Right. Yeah, we'll get into that. He asked if there's a faster algorithm. There is an asymptotically faster algorithm. You know, there's a question of the complexity of implementation on these things. Okay. So here was the algorithm. Either both of them, Karatsuba and the other one, basically did multiplications of these n over 2-bit numbers. Okay, Karatsuba added 2 of them and then did a multiplication of it. Okay. Okay, so the recursion depth was log n, right? Because the size of the number drops by a factor of 2 every time. So you bottom out your recursion when the problem size is 1, and that happens after log n iterations. Okay, so now, again, this is not a log n depth. The speed of this is not log n again. Because when you add the numbers, you could do it sequentially, right? Adding, if you do this carry save addition, that's O of n time. But we saw also in the problem set that you could do this O of log n time if you wanted to be more clever. Okay? So, and the work is the same work as it was for the Karatsuba. Most of the work is done at the leaves. There's no difference here. Because the work at the root is really, it's the same work. We're doing the same work essentially as a sequential algorithm. So all the work is at the leaves, and we do no more work than the sequential algorithm. So we always want to evaluate those for parallel things, the time and the work. Okay, and so the depth, if you do this order n time addition, you get this result. You can actually, and the work is that. You can do log squared by doing each one of these additions in the middle with the binary tree of some form. You do the carries and you do that. Okay? So you could also do better in parallel. Better is possible. Okay. So the one thing to notice is there's actually a better sequential algorithm than Karatsuba. Karatsuba does it in O of n to the log base 2 of 3, which is around n to the 1.59 or something. There's actually an algorithm that's O of n log n, essentially. Okay, so O of n log n. Okay, I put it at the bottom of the slide for a reason, because I can't jump. Okay, so, you know what I'm saying. Okay, so, but there's a little problem here. So this is an open problem, so if anybody wants to work on it, you get rid of this. But, so how do you think, what do you think they did? How do you, what avenue did they use to do this? Oh, come on. Yeah. Yeah. Oh, does it show up? Oh, yeah, they use that. Right. So, and the sorter actually uses FFT network too. It just comes up a lot. It's really a very nice structure. It's a nice algorithm. It encodes a lot of ideas. And this one, using the FFT actually is very natural, because we used FFT to multiply polynomials. Integers are in some sense polynomials. So that's what you have to think about, right? Because you could think of each digit of an integer as maybe the multiplying x to that power, wherever that digit is. And so using that sort of intuition, you can actually get an algorithm like this. And this was done by the same guy who did the matrix multiplication, by the way. So, okay, so now one thing is I said I have a lot of processors. And I did all this work, and I just sort of didn't even care that, how many processors did my laptop have? Well, it had 2, right? And here, what am I'm using n processors, n to the log base 2 of 3 processors, right? It's like, wow, you know, this guy is really reaching, right? He wants his he's talking about all this stuff with his puny little example here. So the question is, what if I have fewer processors? Is all this work I did in terms of analyzing my algorithms and setting up my algorithms, is it worth something? And the point is, do I have to just start again and make a new algorithm for that size of a computer? Okay. So one thing is if I have 2 processors, what can I do? I could just simulate a lot of processors. If you have an algorithm with a lot of processors, I could just have one of the processors in each time step. If I have 2 processors and P processors do something in this time step, I could have one processor do half the work and the other processor do the other half of the work. So that's fine, right? So I can, if some step uses P processors, I can simulate with small p. If I use big P processors, in this many steps, right? I have some rounding error here. So the theorem says any work. So once you come up with a parallel algorithm in this model where you can use as many processors as you want, with work W and time T, I could run it on my little bitty laptop, and my time is going to be this much. It's going to be a scale exactly as you would think it does. I have to pay the same. I have to go at least as long as your infinite processor thing, which is the T, and then I have to go long enough to do all the work you're doing, because the total work is this should be times T as well. P over no. This should be the total work. This should be W over P. Sorry. Okay, it should be the total. I have to run long enough to do all the work you did, so that should be W over P. And then I have to run as long as you did, because even with infinite processors, you took that long. Okay, so it's just clear. Not worrying about the processors too much when you're working to design algorithms is the right thing, because you could always translate it easily. Okay, and this is not maybe how you want to do it. Maybe in practice you want to say, I have 4 processors, let me set it up right. But you start with this algorithm and see how to set it up. Maybe if you knowing that there is a way to do it. Okay? Okay. So let's see what I can do here. Okay, 2 processors, right? I got 2 processors. Okay. I got code. Okay, so there's multiply. Remember multiply? So we did a multiply, and then we put out our answer, right? This is our recursive procedure. Okay. So now I'm going to do a parallel multiply, which basically does the same thing. It splits it up into some number of processors. So in my case, I just go ahead and tell it I only have 2 processors. I don't have to do that per se, but I chose 2 here. Do this funny map, which says this map, you always need a way in your language. You need some construct to spin off your threads. Okay? So, there's in various languages it's different, but in this one, Python provides this tool, which is this library, and what it does is it takes a function, and then it takes an array, and then it applies this function to every one of these elements in this array in parallel. Okay? So it'll spin off a thread to do this function on this pair. Okay? And this function is basically a multiplying x high times y high. Okay? Okay, is that clear? Do people see where the parallelism comes in? Okay. Why do I wrap it? Is that what you're asking? Oh, because multiply takes 2 arguments. This map needs this to take 1 argument. So what wrap multiply does is it takes the 1 argument, unwraps it, and then sends it to regular multiply. If you see, it's just so there's always these things when you do stuff. Okay, this is not an interesting thing. This is not an interesting thing. Okay. But what's interesting is inductions, right? Interesting objects where you really have to think about what you're doing at the code level is FFT, where you're saying, I'm having the coefficients and having the points. That's an invariant. Here, this is another definition of an invariant, right? This is something you need an induction to prove invariance. This is kind of a trivial invariant, right? These functions only take one argument. Okay, so you need to massage it to make it have two arguments. But we work with different kinds of invariants, right? We say, which are also important. So this general focus of, you have this at your disposal. You know how to do this, okay? It's just a higher level thing of the same thing. Well, wrap takes one argument, so let me deal with it. Pool map takes it. Okay, so that's it. So that's really all the meat of this algorithm. So what should I do? Should I run it? Okay. Let's see if I'm in the wrong one. Okay, let's get rid of that. Python. Oh, I didn't do it before. We could pretend I didn't do it before. Okay. I don't know the command, so let me see if I did it before. Okay, so what I'm going to do here, that's too big. I don't want to wait that long. So let me run it. First of all, what does it do? What does the code do? First it does it sequentially, that's just our thing, and then it does it in parallel, and it's going to tell you both, right? Okay, shall we do it? Uh-oh. I guess, okay. Okay. Okay, so I thought this would all take longer, so I'm going to let you go early. So any questions at all? Or yeah. Yeah. So he asked why is the serial one more expensive than the parallel one? Yeah, I think there's a lot of overhead in creating threads and stuff like that. Or I don't know. Yeah. But there's probably something like that.